Welcome to Astronomy 100 Gravity Video Part 2. We're going to focus on Sir Isaac Newton's universal law of gravity and how it applies to the tides here on Earth. Here you have a picture of Sir Isaac. You can see he lived between 1642 and 1727. And when he was around 20 years old, he started working on gravity, and he came up with this, what is called a universal law of gravitation. The word universal because it applies to any two masses, m1 and m2. It's a gravitational force is attractive force. So mass 1 is pulled towards mass 2, and mass 2 is pulled towards mass 1. And the magnitude of the gravitational force is given by this constant g times mass 1 times mass 2 divided by the distance squared, and the distance is measured from the center of each object. So let's have a closer look at how this works for, let's say, the Earth and the Moon. I have a PhET simulation from the University of Colorado at Boulder, and here we have an image of a star, the Sun, and the Moon. This is not to scale because the Sun is much larger in size than the Earth, and it's also, the Earth is located way much further away on the right. But just for the purposes of this demonstration, we're going to assume this is what things look like. Notice that the Sun pulls on the Earth, so this blue arrow here represents the gravitational force that the Sun exerts on the Earth. But also notice that the Earth pulls on the Sun. And one of Newton's laws states that for every force there's an equal and opposite reaction force. So the Earth pulls on the Sun with the same force that the Sun pulls on the Earth. And that's what these arrows here represent. If I turn on a grid, I can see how far apart the Earth is from the Sun. If we play with the mass of the star, let's call that m1. The bigger the mass, m1, the bigger the force. If I change the mass of the planet, we could call that m2. The bigger the mass of the planet, the bigger the force. Notice that the masses or the forces are always equal and opposite. And then finally, suppose I made the distance half as big. In other words, make the Earth 2 times closer to the Sun. What happens to the force that the Sun exerts on the Earth? Ignore this arrow here on the left. Just focus on the force that the Sun exerts on the Earth. If I move the Earth 2 times closer, notice that the force is now 4 times bigger, because here the force goes 1, 2 full squares. If I move the Earth back to where it was originally, now the force is only half of a square. So that sort of summarizes this 1 over distance squared rule. If you make the distance 2 times smaller, the force gets 4 times bigger. If you make the distance 3 times smaller, the force would get 9 times bigger, and so on. So gravity falls off as 1 over distance squared. Now let's go ahead and turn on the velocity here, and let's go ahead and start this orbital motion. And I'm going to turn on paths so that we can follow it, and I'm going to get rid of this grid. Notice that the Earth is always moving along the direction of this velocity v, but it's always accelerating or falling towards the Sun. And as we discussed earlier, an object that is in orbit is always falling towards the most massive object, but it's always missing that object due to the sideways motion. Now suppose I played around with this thing, and let's go ahead and suddenly crank up the mass of the star. Let's do that even more. And let's turn off this gravity force because it's just getting in the way. Notice now that I've got a different shaped orbit. This orbit is now what we call an ellipse. Earth's orbit is almost a perfect circle. And watch, as the planet gets closer to the star, the velocity increases, gets bigger. And as the planet gets further away from the star, the velocity decreases, gets smaller. And if we cranked up the mass of the star even more, you would see this effect even more dramatically. And so you can see from this little demonstration that gravitational, or if an object is in orbit gravitationally, it's going to form an elliptical shape Sometimes an ellipse looks just like a circle, but most of the time they look like squash circles. All right, that's enough for this demonstration. Let's go ahead and hide this guy and come back to where we were. And notice the simulation. If you increase the mass of 1, the force got bigger. If you increase the mass 2, the planet, the force got bigger. And if you change the distance, the force changed as 1 over distance squared. You got to remember to square that distance there. Now let's apply this to the moon. Here we've got Newton's law of gravity, which falls off as 1 over distance squared. That means if you treat the moon as one mass, this near side of the Earth, the gravitational force of the moon is going to be larger than it is at the center of the Earth. And as a result, the waters are going to flow outwards towards the moon roughly. On the far side, the Earth is being pulled to the right more than the waters are being pulled, so the bottom is pulled out from below, and you end up with a second bulge. And so here we have high tide, low tide, high tide, and low tide. Remember, the Earth is spinning counterclockwise, so as the Earth spins, the tide is coming in. Now it's high tide, the tide is going out. Low tide, the tide is coming in. High tide, the tide is going out, and so on. So Newton's law of gravity explains why you have 2 tides a day. It also turns out the sun's gravity plays a role in the tides. If it's a new moon or a full moon, then the sun, moon, and earth are aligned, and that means the gravitational pulls will also work together. And so you'll end up with really high tides and really low tides. And we call these spring tides. They have nothing to do with the time of year. So they just call them spring tides. So new moon and full moon, the high tides are really high and the low tides are really low. Now at first quarter moon and third quarter moon, the sun's pulling one way, the moon is pulling 90 degrees to that direction. Now the gravitational pulls are working against each other. And as a result, the tides will not be nearly as extreme. And we call these neap tides. So for neap tides, the high tides are not very high and the low tides are not very low. And these occur near first quarter and third quarter moon. That's a little more complicated than that because remember the Earth is spinning. And so because of this spinning motion, it turns out the tides aren't exactly lined up with the moon. And in fact, high tide is just a little bit offset from a line from the center of the Earth to the moon. What this means is that this part of the Earth tugs on the moon a little harder, and then what that happens is that the moon gets pulled forwards in its orbit a little more, sort of like you're slinging somebody around in a circle. And as a result of this offset between the high tide and the direction towards the moon is actually being accelerated a little bit, and the result of that is the moon is slowly moving away from the Earth. But it's a tiny amount, a few centimeters a century if I remember right. So if we wait long enough, millions and millions or even 1 billion years in the future, the moon's actually going to be much farther from the Earth than it is right now. All right, so to remind you, Newton's universal law of gravity depends on the product of the masses and 1 over the distance squared between the masses. That's it for now. Have a good day. Have a good semester.